Hello. From this video, we are going to discuss serious statistics. The title of this part is sampling distribution. So this is the goal of, ultimate purpose of, almost every statistics theory. So sampling distribution is, so basically, simply speaking, what we want to do here is to know the distribution of the estimation error. We know that an estimator cannot be perfect. It it will have errors all the time. So we cannot. So there is to remove the error. The only possible way is to make to have an infinite number of observations, which is not possible. So that's impossible. Then let's admit that, acknowledge that we need to live with errors. Then what we can do there is at least let's study the distribution of the error. Fortunately, the distribution of error is well known. If you understand statistics, you can calculate how the estimation the errors how the errors will be distributed. So that's what we are going to do here. And before we start, let's think about how the sampling distribution is defined. Remember, whenever I define a distribution, you have to think about the underlying random experiment. Random experiment is like throwing a dice, tossing a coin, or choosing a random person. These things are random experiments. So distribution is generated from when you repeat experiment many times, then the results, the outcomes from many experiments will be different across experiments. So the result from the first trial and the second trial and the third trial would be different. And when you collect those outcomes, different outcomes, many times by repeating the experiment, you are going to see a certain distribution. That is the distribution, right? So you know what is a distribution. I just described what you have in mind. So remember, the point is experiment and repetition. Then, now, I'm going to consider a very special experiment that we have in mind. So, a statistician's job, say for example, I would like to estimate the mean, the average of U Albany students GPA. So average U Albany students GPA. Then what I can do there is now I'm going to randomly choose 100 students, say from the database, say the university database. Suppose that it's available, I can access to the database, and say I randomly choose 10 students, U Albany students, and I say 100 U Albany students, and then using the 100 U Albany students, I will calculate their average GPA. The average of their GPA is over 100 students. Then that average GPA will be my estimator. This is one experiment. Let's repeat this. I say in the first estimation, I got an average GPA of 3.0. So suppose that my estimator was calculated as 3.0. So let's do the second iteration. What I'm going to do is now I'm going to throw away the 100 students that I used in the first trial. And from the database, I will choose 100 students again with replacement. Put the original students back into the database and resample 100 students and recalculate their average. Then this average may be different from the first one. So this is the outcome from another experiment. So I have done 2 repetitions, and I can do the third one. Just collect 100 students again from the database. So collecting 100 students is one experiment. So usually we take it as 100 experiments, but no, now I will take it as one experiment collecting 100 students, and the result of that experiment is the average of 100 students' GPAs. So then, in our mathematical notation, so drawing a random sample of size n is one experiment. As a result, we have n number of students' GPAs, right? I choose n observations and calculate just one estimator from those observations. So the calculated estimator is the only outcome from one random sampling. One sampling generates one estimator. So that is one time experiment. Imagine in your mind, you can repeat that experiment again and again. So every experiment generates one value of estimator. Then if you can repeat that, of course it is not possible in practice, but like just hypothetically you can repeat that, then you will get many different values of estimators for the same parameter, and they will make a distribution. That is the sampling distribution, right? Then why is it important? Almost every statistics theory you know is based on the sampling distribution. For example, the bias is the average of the expected value of this theta hat over the repetitions, right? Bias is about the mean of the distribution, and the variance of the sampling distribution is the efficiency, standard error. So variance, the smaller the variance on the estimator is, the more efficient the estimator is. So that variance is the variance of the sampling distribution. And standard error of the sampling distribution is the standard deviation is called the standard error. The standard error is the standard deviation of the sampling distribution. And confidence interval is calculated from the sampling distribution. So if you have a sampling distribution and if you choose an interval, then the probability on that interval must be the confidence level, like 90%, 95%. Also, the hypothesis testing is based on the sampling distribution. Like p-value is calculated based on the sampling distribution, and like type 1 error probability, type 2 error probability, all of these guys are calculated from the sampling distribution. So sampling distributions are important, and this is usually sampling distribution. Knowing the sampling distribution is like enough. Like that's what we want, and from there it's pretty obvious. Like calculating the mean, calculating some probability on the sampling distribution. So that's relatively a minor problem from there. And so and I understand that it looks very complicated. So like all of these guys, like bias, efficiency, p-value, p-value, like type 1 error, power, these things look difficult, complicated, but forget about them. But the only point you need to understand is the sampling distribution. What is the sampling distribution? How we get there. So okay, now then I will really start the serious discussion. So follow me. So now let's think about an estimator theta hat and the true parameter theta 0. So first of all, the first thing for an estimator to be good, so a good estimator must be consistent. It's pretty much the minimal requirement for a reasonable estimator. If something is not consistent, then so need to think about that again. Anyhow, consistency is defined in this way. The arrow subscript p is convergence in probability. Simply speaking, you can read it as in casual words, I'd say the estimation error converges to zero as the sample size increases in the limit, right? So that's the most easiest level interpretation. And I hope you to understand what the convergence in probability means and how it is defined. I believe you learned them in Econometrics 1, or we are going to, maybe, I hope so. But if not, if you are not familiar with that definition, then alternatively, you may think it this way. The mean converges to the mean of the expected value of the error converges to zero as n increases to infinity, and the standard deviation of the error also converges to zero. And so this convergence, by the way, these two convergences imply mean squared error convergence, which is different from the probability convergence, but usually it implies the convergence in probability. So if you are not smart enough to understand the convergence in probability, this is a good alternative. But then you have a big problem in your PhD life. So go back and read the textbook to see what is the definition of a convergence in probability. Okay, I'm going to continue in the next video. See you later.